Hello everyone, welcome to the 16th episode of this series. In this video, we'll talk about characteristic polynomials. So last time, we learned about eigenvectors and eigenvalues of a matrix. We learned how to find eigenvectors given a particular eigenvalue. But like in this episode, I want to talk about eigenvalues. In particular, how can we find the eigenvalues of a given matrix A? That is, if we have an A and some number lambda, how can we tell if lambda is an eigenvalue of A, or in other words, if lambda eigenvectors exist? So we're going to start off with two observations. The first observation is that the condition A minus lambda I times V equal to 0 always has at least one solution because it's a homogeneous system, and the solution is the zero vector. But it does not count because we want the eigenvectors to be non-zero by definition. So if this matrix equation has at least two solutions, then A has a lambda eigenvector and lambda becomes an eigenvalue of A. And the second observation is that A minus lambda ID is a square matrix because A is a square matrix, and therefore the matrix equation given by A minus lambda I times V equal to 0 has a unique solution precisely when A minus lambda I is invertible. So when it's not invertible, this matrix equation is going to have more than one solutions, and that's what we want. And using the relationship between invertibility and determinant, we get that lambda is an eigenvalue of A if and only if the determinant of A minus lambda times identity is 0. Let's look at an exercise. We're given a 2 by 2 matrix with entries 1, 5, 5, 1, and we have to find the eigenvalues of this matrix by solving the equation, the determinant of C minus lambda times identity equal to 0. So first, we're going to compute C minus lambda times ID. So, we know what C is, we know what identity is. We get 1 minus lambda, 5, 5, 1 minus lambda. And when we take its determinant, we get 1 minus lambda squared minus 25, and that's just minus 24 plus lambda squared minus 2 lambda. Now, because we have to set this determinant equal to 0, we get that minus 24 plus lambda squared minus 2 lambda is 0, which upon solving gives us that there are two eigenvalues. One of them is minus 4 and the other one is 6. So our main tool in the previous exercise is an important idea, and it has a name like most important ideas, and it's called the characteristic polynomial of a square matrix. So given an n by n matrix A, like the function of x or lambda if you want, given by determinant of x times identity minus A, is a polynomial of degree n, and as I said before, we call it the characteristic polynomial of A. For example, C is this 3 by 3 matrix. Its characteristic polynomial is going to be the determinant of x times the 3 by 3 identity matrix minus A. So we've already computed that here. And its determinant is going to be my characteristic polynomial PC for my matrix C. So to compute the determinant of x times identity minus C, we can just use the cofactor expansion along the third row. So we get x minus 2 times minus 1 to the 3 plus 3, and the submatrix we get upon deleting the third row and the third column is x minus 2, 1, x minus 3. And it's a 2 by 2 matrix. You know how to compute its determinant. It's x minus 2 times x minus 3 plus 2. And the rest is just multiplication, and we get x cubed minus 5x squared plus 8x minus 4. So the reason the idea of a characteristic polynomial is important is because we can restate our criteria for eigenvalues using the characteristic polynomial more explicitly, the eigenvalues of a matrix A are the roots of the characteristic polynomial of the matrix A. Let's look at an exercise. So we're given a 2 by 2 matrix, and we want to find the eigenvalues of this matrix. Okay, so the characteristic polynomial of A can be computed by computing the determinant of x times the root times 2 times 2 identity minus the matrix A. So we get x0, 0, x minus 4 minus 2 minus 1, 3. That just becomes x minus 4, 2, 1, and x minus 3. And its determinant is just going to be x minus 4 times x minus 3 minus 2, which upon simplification is just this quadratic expression, x squared minus 7x plus 10. Now, remember that we want to find the roots of this polynomial. Now, the ax can be factored as x minus 2 times x minus 5. So when you set this equal to 0, we get that there are only two roots, x equal to 2 and x equal to 5, and those two are the eigenvalues. So this matrix A has eigenvalues 2 and 5. Okay, so next we'll go one step further, and we are going to find all eigenvectors for the two eigenvalues that we just found for the 2 by 2 matrix. So recall that to find eigenvectors for a given eigenvalue, we try to find non-zero solutions to the matrix equation given by lambda I minus A times V equal to 0. So the next exercise is, of course, finding all the eigenvectors of the matrix 4, minus 2, minus 1, 3. So from exercise 2, A has two eigenvalues, 2 and 5. We are first going to work with 2. So to find two eigenvectors of A, we replace lambda with 2, and we get this equation. And to solve this, we have to solve the matrix equation given by minus 2, 2, 1 minus 1 times xy equal to 0, 0. Now, there is an augmented matrix corresponding to this matrix equation where we put the coefficient matrix on the left side of the separator line and the constant vector on the right side. Now, the first thing we do is we switch row 1 and row 2, and then we multiply row 1 by 2 and add it to row 2, and we get we get a matrix in a row echelon form, and we can clearly see that the second row has no leading ones. So that means there are going to be more than one solutions. And note that this first row now corresponds to the equation x minus y equal to 0, which just means x equals to y, and therefore all the eigenvectors with eigenvalue 2 are going to be of the form t comma t, or a vector given by t, where t is any non-zero number. To find the 5 eigenvectors of A, we replace lambda by 5 in a similar fashion. We are going to solve the matrix equation given by 1, 2, 1, 2, vector xy equal to 0, 0, where this matrix 1, 2, 1, 2 is achieved by just multiplying 5 with identity matrix and then subtracting the matrix A from it. And like before, this matrix equation corresponds to this augmented matrix. We see that both the rows are exactly the same, so we can just subtract the first row from the second. And now the first row just corresponds to x plus 2y equal to 0 in the linear equation form. So therefore, there are going to be more than one solutions to this, and the 5 eigenvectors of A are going to be of the form minus 2s s, where s is a non-zero number. So we took y to be a parameter s, and that gave us that x is minus 2s. And with this, I would like to end this episode. Hopefully things were clear. I will see you in the next episode. Up until then, happy learning.